In the course, there are two equations that appear for angular momentum, r cross p and I omega. Sometimes you will see mrv as well, but that is a special case of r cross p. When should you use each equation? When do they apply? And to what do they apply? We will talk about this, and in discussing this, we will run across the famous angular momentum decomposition into spin and orbital components. The answer is very simple. Either equation will work for calculating angular momentum of point particles, but if you want the angular momentum of a purely rotating rigid body, a rigid body only undergoing rotational motion, not translational, you must use L equals I omega. So point particles, either one, rigid bodies, I omega. If you recall how L equals I omega was derived for rigid bodies, then you will clearly see this as well. A rigid body is a collection of point particles, each of which has angular momentum of r cross p. And then when you add it all together, we ended up with L equals I omega. Another difference between the two formulas is when they are true. L equals r cross p is true about any reference point. And as usual, you place your origin at the reference point. Meanwhile, L equals I omega is only true in some cases. The details and assumptions of that are discussed in another video. Or in other words, L equals r cross p always works, but L equals I omega only in some cases. So why do r cross p and I omega both work for point particles? Well, the intuition is that a point particle is a rigid body consisting of one particle. Recall, we have a rigid body. It's made out of a bunch of point particles. In the limiting case where the rigid body is just one point particle, well, there we go. Rigid body with one point particle, so we could use I omega or cross p to calculate its angular momentum. You could also do a little bit of math to see that both equations work for a point particle. Just start with r cross p. The linear momentum p is just mass times velocity. Multiply and divide by r squared. And then we have this r cross v over r squared. That's just angular velocity omega. And this mr squared, and that's the moment of inertia of a point particle. You could also go the other direction and start with I omega and plug in the moment of inertia for a point particle, which is mr squared, and work your way back to r cross p. It turns out, though, that the r cross p formula isn't completely irrelevant for rigid bodies. You can decompose the angular momentum of a rigid body into a spin and an orbital component. All you have to do is think about the rigid body's center of mass, and a rigid body, therefore, could have both forms of angular momentum. Think, for an example, of the Earth orbiting the Sun. It spins about on an axis through its center of mass, and the center of mass moves around the Sun. We have a spin component of angular momentum, the rotation about the axis through the center of mass, and an orbital component of angular momentum, the center of mass moving around the Sun. And so we see in this picture here, here's the Earth orbiting about an axis through its center of mass. Meanwhile, the center of mass is undergoing a circular orbit around an axis of rotation that is through the Sun. So spin angular momentum and orbital angular momentum. The Earth has both. This decomposition then is decomposing angular momentum into two components. There's a component of angular momentum about the center of mass and a component of angular momentum of the center of mass about another axis. Using the Earth-Sun example again, here's the component of angular momentum about the center of mass, the Earth spinning about its axis. And here's the component of angular momentum of the center of mass about another axis, about the Sun. As it turns out, the r cross p momentum is the orbital angular momentum of the center of mass about another axis, and the I omega momentum is the spin angular momentum of the object rotating about an axis through its center of mass. And so both formulas will be used in calculating the total angular momentum of a rigid body when using this decomposition. Noting that, we have another explanation of why both I omega and r cross p can be used to find the angular momentum of a point particle. A point particle rotating about a point can be viewed as either orbiting around the point, or it can be viewed as a one-particle rigid body that is spinning about its axis of rotation. The ambiguity of what a point particle is doing, is it spinning, is it orbiting, that helps us also see intuitively why both r cross p and I omega can be used for it. It just depends on your perspective, whether you view it as spinning or orbiting. Altogether then, here is the precise statement of the decomposition of angular momentum. We see we can break it into a part that has the moment of inertia about the center of mass times omega, I omega, plus a part that has the angular momentum of the center of mass. So we have the linear momentum of the center of mass about another point, which this r vector will be drawn from. So this is the vector from the reference point to the center of mass, and then this is the linear momentum of the center of mass. R cross p, that is the angular momentum of the center of mass about the reference point. We call these the spin and the orbital angular momentum. And so we therefore see both I omega and r cross p are applied to any object, including rigid bodies, if we think about them as decomposing the angular momentum into spin and orbital components. What I have talked about here is decomposing angular momentum of a rotating body into two components, but it turns out this points to something even more general. For any rigid body motion, you can always break it into two components, a rotation about the center of mass and the translational motion of the center of mass relative to another axis. And that center of mass could be rotating around that other axis, or it could just be translating. You can kind of understand this a little bit from what we have learned by recalling how angular momentum can be defined for straight line motion. So this r cross p term doesn't necessarily imply that the rigid body is rotating about another axis. It could just be moving in a straight line and translating. It'll still have this quote unquote orbital component of angular momentum when translating. And so that can help you see how this statement is true from the decomposition that we already have, namely r cross p doesn't have to be a rotation, an orbital motion, but it could be translational. And so that is the general statement for rigid bodies, although we won't delve any deeper into that. Okay, after talking about all that, let's see an example. This decomposition doesn't require an object to actually have orbital and spin components in any natural sense. Instead, they just need to have spin and orbital components about some other reference point that you have chosen. Let's suppose that we have a rotating rod and it is rotating about its end, being constrained to rotate there. Maybe there's a motor that's making it run, I don't know, but it is rotating. Okay, so let's now calculate the angular momentum about this reference point, about this axis of rotation about which it is rotating in two different ways. First, let's calculate it directly using the parallel axis theorem. Then I will use the decomposition of angular momentum into spin and orbital components to calculate it, and we will see that they result in the same value. So firstly, the moment of inertia of a rod rotating about its end, if you use the parallel axis theorem, is where L is the length of the rod and M is its mass. This is one of those cases where we can use the L equals I omega formula for angular momentum. And so we see the rod has that amount of angular momentum about its end. Let's now calculate the angular momentum using the decomposition. Okay, so first we need the moment of inertia of a rod about its center of mass. And then we need RCM. We need the position vector from the axis of rotation to the center of mass. So that will be that. And then we need the momentum vector of the center of mass about the axis of rotation in red. And here we have it. At this point in the motion, that's where it will be pointing. We can see from the symmetry that the position vector and the momentum vector will be perpendicular to each other, which will help simplify the cross product. We can see that RCM is just going to be half the length of the rod. And the linear momentum of the center of mass is just going to be mass times velocity of the center of mass. These are their magnitudes. When we take the cross product, we got to do the right-hand rule. So first, imagine taking the center of mass vector and making it come from the same point, emanate from the same point as the position vector. Fingers go in direction of R, curl towards P, and you'll see that your thumb is sticking out of the page, or in other words, angular momentum for R cross P is going out of the page. Okay, let's put it all together then, where K hat, the positive Z direction, I understand to be coming out of the page. Then note the relationship between linear velocity of the center of mass and omega, which is the same for all points on the rigid object. They all have the same angular velocity omega. To calculate the linear velocity of the center of mass, we need the distance of the center of mass from the rotation point, which is just RCM. And then we multiply by the angular velocity of the center of mass, which is omega. But RCM, again, is just 1/2 L. So let's plug this in. What do we get? So in this first step right here, all I did is I plugged in omega times 1/2 L for the velocity of the center of mass. Then I combined like terms over here. 1/2 L times 1/2 L is a quarter L squared. Moved my m around to make it look better. Then omega times k hat, that's just the direction of angular velocity. The rotation is counterclockwise. Angular velocity is also going in the positive z direction, the k hat direction. So I combine the magnitude of angular velocity with its direction into just the angular velocity vector omega. I can now combine like terms. Then a 12th plus a quarter, creating a common denominator and all that, you'll see equals just a third. And so we see we get the same expression either way, thereby verifying and also showing how to use the angular momentum decomposition for calculating angular momentum of a rigid body about any reference point. If this looks similar to the parallel axis theorem, the two are indeed connected, but I will leave the details out of this video.